Here we have another typical GMAT problem. It's a pretty word-heavy problem, so we want to read it carefully and then sort of see what we're dealing with. It'll actually deal with a little bit of mental math, and we'll see how we can kind of create some shortcuts to make it easier on ourselves. So let's read it. An entire hockey team goes out for a post-game dinner, and the bill comes to the table. The total, including tax and tip, is $753.75. If each player contributes at least $35, what is the maximum number of players on the team? A couple things I would highlight right off the bat is at least $35 everybody's contributing, and max number of players on the team. We know we're trying to get to a bill of $753.75, and because they say tax and tip is included, I'm going to assume that they're not going to pay more than that. So they're just going to pay up to that value. So given that, we could say the maximum number of players on the team. So how do we figure out the maximum number? Well, let's say, let's just go with a very simple example and say that the bill was actually $75. Now, if there was one player on the team, we know they're paying at least $35. If there's two players on the team, we know they're paying at least $70. I'm just multiplying by 35. And if there are a max of 3, we know they're paying at least 105, because that's another 35 on top of here. Well, we know that 105 is greater than 75, and we're not going to pay more than 75, so it can't be 3. 70 is still less than 75, so there could be 2 players. There could be 1. They would just have to pay more per person, but in this case, the maximum number would be 2. So in other words, we're trying to get to this number of players where when we multiply it by the minimum that they're going to spend, which is 35, we get to a number that's slightly less, or I should say as close to the bill as possible without going over. So 70 is close to 75, but 105 is over 75, so we know it couldn't be 3. So we're going to do the exact same thing, only with $753.75. So we said our bill now is $753.75. We want the number of players times the minimum that they're spending, which is 35, to be as close to, but not going over, $753.75. So I'm going to say we need it to be less than that, but only within $35 of it. So let's look at our answers now. We have 18, 19, 20, 21, 31. When we're multiplying 2 digits by 2 digits, it's easiest to take one that starts, or that ends, I should say, with a 0. So I'm going to start with 20. The reason that's easy is because we're doing mental math here. 20 times 35. You can forget the 0 for now and just do 2 times 35, which is 70, and then just add the 0 on at the end. So we know that 20 times 35 is $700. If they had 20 players, they're paying at least $700. That is less than $753.75, but we can see quickly, hopefully, that we can add another player times 35. We don't have to do the math here, it's just adding 35 onto 700. So this would be 735. Great, we're still less than $753.75. So there could be 20 players, there could be 21 players. Obviously right now 21 is higher than 20. So right now that's our best answer because we're looking for the maximum number. Then you could go to the next highest and you would say, well, the next answer is 31. We know that's going to be way higher, so we probably already know our answer. But even if you just added one more player, even though that's not an answer, times 35, we would add another 35 onto this amount. So 735 plus 35 is 770. And we can see that that's greater than 753.75, which is no good. We didn't want that. So 22 cannot be a number. So it can't be higher than 21. So our maximum number of players is 21, which is part D. The key to this problem was understanding how at least $35 and maximum number of players intertwined, I guess. You want to get as close to 750, 375 without going over. Reading that question carefully is the first key, and then understanding your mental math to not spend too much time on multiplication. Start with 20 and then go either side of that.